So in the last classes we discussed about the different loss functions of neural network, and we discussed how similar this was to machine learning losses, right? So finally we have completed one basic neural network structure, which is what? A multi-layered perceptron. We went over all the concepts of optimizers, layers, activation functions and everything. So we completed multi-layer perceptron. Now that is a good thing that we have completed this. So we can now look into how we can code a multi-layered perceptron. First of all, let us look into how we can do this. Basically there are three main frameworks to actually code for deep learning. So why this is important is you need to understand it's not easy or it's not feasible for us to write code for every little thing, including activation function or optimizers or let's say losses and everything. So what these frameworks do is they make it easier for us, so we don't have to write each and everything. Okay, so what are the three main frameworks? First of all, we have TensorFlow, we have Keras, and we have PyTorch. So PyTorch is the most relatively new framework, and it is totally based on Python. This was released by Facebook. So the thing is, for now we will not discuss about PyTorch. Let us understand the differences between TensorFlow and Keras, right? So let us start with Keras. So what Keras is, basically it is a high level framework. TensorFlow is a low level framework. So what that means is, suppose you are writing one full function in TensorFlow just to define a particular thing, you'll have to write maybe just a single line for that in Keras. So it makes you write less code. So that is that. Keras is beginner friendly. So what that means is, if you start, even not just beginner friendly, it is also user friendly. So what it means is, when you start doing it or anything, it is very easy to understand Keras. However, it takes a lot of time to understand TensorFlow. So it is not, I'm just writing user friendly for now. Although it's not beginner friendly also. So whenever a person starts it, they always prefer to go through Keras first and then shift to either TensorFlow or PyTorch. Okay, then Keras is the most used framework out of all these three. Now the reason for this is because, like I said, it is very beginner friendly. Also it is easy to debug. So if you have some mistake or you have done something wrong, it is very easy for you to understand that in Keras. However, it's very difficult to understand it in TensorFlow. So again, this is the second most used framework. Again, the reason for this can also be because PyTorch is very recently introduced. These were there before PyTorch, and yeah, it is a bit difficult to debug in TensorFlow. Okay, now these were all the pros that we looked into Keras. Now let us look at some of the cons as well. So what are the cons? Well, first of all, it is faster in TensorFlow compared to Keras. Now why is that? Is because TensorFlow is built on C and C++, but Keras is built on Python. So everyone might have heard of this or maybe known this, that C and C++ is basically faster than Python. Okay, so that is one of the cons. The other con is TensorFlow is very flexible. So what this means is, suppose you have to make a very minute detail, or you have to make a detail, you have to make a change which is very much in the core of the layer or a model or something like that. It is very easy to do that using TensorFlow and not in Keras, because like I said, for TensorFlow you have to write an entire function, but in Keras you just have to maybe import a library or maybe write a single line. So that single line of code has already been given in, let's say, the framework or something, so you cannot change that. However, if you are writing a function, you can make a lot of changes. So what that means is, you can change very little things in TensorFlow, but you cannot do that in Keras. Okay, so now that we know that, let us go and understand some other things, right? So what we will do right now is we will understand a code for Keras which explains a multi-layered perceptron, right? Okay, now we are starting with Keras. The reason because is it's very easy to understand Keras, like I said, so we can begin there and later on we can skip to TensorFlow and PyTorch as well, but for now let us keep it to Keras. So the task is to create a multi-layered perceptron. What is the problem statement? Basically we will be working with the MNIST dataset. So what is the MNIST dataset? You might have heard while learning machine learning, whenever you are starting any topic or anything, you always used to try it on IRIS dataset, right? IRIS dataset was a classification problem, like okay, yes, it was a multi-class classification problem. So in the same way, MNIST is used for deep learning, and it was known as, I remember, something like Hello World. It was very similar to Hello World for machine learning. So in the same way, MNIST is basically very similar to Hello World for deep learning. Okay, so what exactly is the MNIST dataset? First, let us go over that. So in MNIST dataset, you have some pictures, some images, right? You have some images which are of 28 cross 28 dimensions, and in this are handwritten numbers. So you have, let's say, 0. So you have a handwritten number here. So the main task of our code should be to identify that picture and identify the number in it and give out which class it belongs to. So we will have classes from 0 to 9, and we have handwritten numbers for 0 to 9 in images. So from the image, the model has to understand which number it belongs to, right? Okay, so now let us go and see the code itself. So before we start anything, obviously we have to install Keras. So this is the statement to install Keras. You have pip install Keras. Like in my case, I have already installed Keras, so it says requirement already satisfied. Here this gives which version of Keras I am using, which is I am using 2.4.3. Then the next statement is obviously importing some models. So for the first thing, I am importing matplotlib. This is because I just want to plot out all these numbers that I mentioned here and show you how they actually look, right? So I am importing matplotlib to display the images. And yeah, the main thing to understand or remember in Keras is basically this layer submodule. So if you remember, here you had layers, right? This was the input layer, this was hidden layer, then you had output layer, right? So this layer submodule in Keras is basically to import these or write these layers. Okay, and we have models, which is basically what kind of models we want, but for now let us just keep it to sequential. So let us import this as well. Okay, so once that is done, now what we will do is load the MNIST dataset here. Okay, so in IRIS also we used to load the dataset from scikit-learn, right? So here also we will be loading the dataset, but we will be loading it from Keras. Where? From Keras.datasets. So this is already defined dataset in Keras. So we load this dataset. We have xtrain, ytrain, xtest, ytest. Okay, so let us, for example, say we want to understand the shape of xtrain. So the shape of xtrain is 60,000, 28, 28. Okay, first let me break down what this means. So we have 60,000, 28, 28. like I mentioned, this 28, is basically the dimension of the image. So you have 28 pixels as height and 28 pixels for the width. 60,000 basically means we have 60,000 data points for training. So you might have heard for deep learning you require a lot of data, usually most of the time. So you have 60,000 data points. That means you have 60,000 handwritten numbers. Okay, so that is basically what the dimension means. Like, let's check this out for X test. So this has 10,000 data points. So the same thing, but for testing you have less data. So yeah, it has 10,000 data points. Let's check this out for Y. So we have 10,000 for Y test also. Again, since we had X test as 10,000 data points, so we have 10,000 labels, but you have no other dimension here, which means it is just 1. So what your actual thing will look like is, let's say we have to understand what Y test look like. So we can do like this. So it is basically an array which contains the output, the labels, right? And then here these are just basic codes. So this is matplotlib, and I'm doing this just to show you how it looks like. So if I change this to Y train, you'll be able to see it is 504, just like here. So you have X train, and X train looks like this. These are handwritten numbers. So you have a black background and this is written by hand. So these are all handwritten numbers, and from these images we have to get these outputs, right? Okay, so you have this, but you might have known this in machine learning also, that you cannot actually work with labels like numbers like this. So the best thing that you can do is change it into a categorical value. So what basically toCategorical does is changes this into a categorical value. So what that means is, let's say you have 3 as the label. What happens is it converts this into a 10-dimensional output, and it will look like 0, 0, 0, 1, 5, 6. Okay, so this stands for the 0th position. This is for the first position. This is second. For the third position, since the output is 3, so we have this here 1, and then the rest is 0 again. So this is what toCategorical does. So since we cannot use these labels as they are, we will convert this into categorical values. Hence we convert the Y train and Y test to categorical. Now let us check the shape. So let's check the shape of Y train. So 60,000 data points, but now here you had 60,000. Here you had 60,000 comma nothing, right? And here you will have 60,000 comma 10, because we have just converted into categorical values. Okay, so these are basically what you have learned, nothing new here. But yeah, now comes the new part. So we have the model part. So the first statement is to write a sequential model. So what sequential means is all the layers are one after the other. So one after the other we have the layers. So that is why we have to define that a model is a sequential model. Next thing, now we will add the layers to the sequence. So we have first flatten, and then followed by 2 dense, and then there is also a third dense. So first let us talk about flatten. So what flatten does is, basically you had this 28 cross 28, right? You had all these pixels here. So let's just imagine like this for now. So you had these pixels here. What flatten does is basically flattens this out. So this is 2 dimension for now, but if we flatten this out, this will become 1 dimensional like this. So let's say we had 1, 2, 3, 4, 5, then 6, 7, 8. So what this will happen, turn into is 1, 2, 3, 4, 5, and then 6, 7, and this will go on till here. Let's say this is the 10th value, so 10. Okay, So it basically flattens out. So if you had 28 cross 28 as a dimension, 2 dimensions, so this will become 1 dimension and its value will be 28 cross 28. So whatever is the multiplicative value of this, so I guess this is something across 784. So whatever it is, so basically the thing is this gets converted into a 1 dimension of this size, 28 cross 28. So that is what flatten does. Now the reason why we are flattening this is because we are using a multi-layered perceptron. So multi-layered perceptron just takes one input. It does not take anything which takes more than 1 dimension into consideration. So that is why we have to flatten this. We will come into more models which take different dimensions into consideration, but for now, since we are using only an MLP, so we will flatten this out. Then we will be adding 2 dense layers and the activation is sigmoid here. Now these 2 dense layers are basically the hidden layers here. Okay, so this is here 10 means it has 10 neurons. So this will be equal to, here we have 4, in this case we have 10. And in the next part we have the same but 5 neurons. So this is not 2 but 5 neurons. Okay, so that is what dense does. So what dense basically means is all these are very fully connected. Like here you see all the networks are fully connected. All the nodes are, all the outputs from the nodes are going into the next layer nodes, right? So that means it's fully connected. So here dense means it is fully connected. Okay, and activation sigmoid is basically, if you remember, this was again divided into 2 parts. You had an activation function and you had a summation function, and then it was followed by an activation function, right? So yeah, the activation function here is sigmoid. That is what this whole line of code means. So you are adding 2 dense layers of sigmoid, and the final layer you are adding is a softmax layer. So first you should understand this is a classification problem, a multi-class classification. So you have these images and the labels are from 0 to 9, right? So this is a multi-class classification problem, and for classification problems we usually prefer, for more than one class we usually prefer softmax layer. So that is why the activation in the final layer is softmax. So this is our final output layer and the activation here is softmax, right? Okay, so this is our model structure, and now let us look into the model.summary. This helps to give a summary of the model. So we have a flattened layer, like you see it's 784. I guess I wrote 784. So 784 basically means 28 cross 28. So the first layer is a flattened layer, then we have dense layers, 2 dense layers, and a final output layer. So this calculates a total number of parameters. What params means is basically the number of weights plus biases we will be training. So like you can see, even in such a small model we have 7,900, around 8,000 parameters to train, right? So this is the model. We have defined the architecture of the model. So Keras also provides us with this option of plot model. So what plot model basically does is it shows you how it will look like. So it gives you an output, an input, an output. So it gives you an input and an output. So the none here means how many we will go in and train in batches. So I will explain that, but yeah. So we have 28 cross 28 as input layer. We have a flattened layer. So the 28 cross 28 gets converted into 784. Then the 784, since we have 10 activations, so the output will also be in the size 10. And then we have 5, that is the number of neurons. So we have 10, 5, then 10. So that will be how the output will be, 10, 5 and 10. So what this none is, we'll come across later. So once the architecture has been defined, we will compile the model. So this is where you define what kind of loss and optimizer you will be using. So you need to understand, since the problem is a is a multi-class categorical problem. So the loss we will be using is also categorical cross entropy. The optimizer we will be using is Adam, and what are the metrics that we will be using is accuracy. So how accurate the model is. So we have actually defined the architecture of the model, we have compiled the model. So the final part that is left is to train the model. So to train the model, there is just one simple line of code that you need to write. This is model.fit. In model.fit, you will input the x value for training, the y value for training, the number of epochs. If you remember, the number of epochs is basically equal to this, moving forward and then again moving backward, right? So this is the number of epochs. This is one epoch. Moving forward, updating the weights, and then going back, updating each of the weight. Then again moving forward is another epoch. So we will do that for 20 times, and then we have validation data here, x test and y test. So yeah, so now that is done, we will run this. So after running, so this takes some time, so I'm just going to show you the outputs that I have. So this gives a very extensive detailed output on what is happening. Okay, so this is for the first epoch. It runs for 1875. I'll explain what this 1875 is. So it took 2 seconds to run and 1 millisecond for each step, and the loss is 0.49 accuracy, and now this loss and accuracy is basically for the training data. So accuracy is 0.85, very good from the start. The loss is for validation is 0.51 and accuracy is 0.84. So our main goal will be to reduce the training and validation loss while increasing the accuracy of training and validation. Okay, now let us come back to this mysterious none and 1875. When I said that you have the training data and the input goes in here, I never mentioned what kind of input will be going or how we will be training or sending the input. So there are a lot of ways to actually send the input. Suppose you have one value and you are sending the whole value and then you are updating. So that is one way, but you can also send in batches. So that means you can send multiple, since you have 60,000 data points. You cannot send the whole 60,000 at one go. Your RAM might not be able to handle so many data points and so many training parameters at once, right? So what you can do is, instead of sending the whole 60,000, you can send it in batches, like batch stochastic gradient, if you remember. So here what will happen is, you will send it in batches. By default, the batch size is always mentioned as 32. Since we have not defined any batch size, so the model does not assume anything and gives a none output. Here, once the batch size is defined, this will change, the value will change, and this will give the batch size that we are using. So it is usually multiples of 2, not exactly multiples but powers of 2. So we have 16, 32 and so on. By default, the model always assumes, Keras always assumes that we are using 32. If we are not giving anything. So there are two things actually which actually get me very confused all the time. So one is, in model.fit we have number of epochs and then we have steps per epochs. So these are two parameters that you get, and it is very confusing to actually understand this. So I'm explaining. Epoch is basically, you have the model, you move forward and then backward by updating the weight, that is one epoch. Steps per epoch is how you will be going in with the input. So you have a batch size of 32, right? So that means you have, let's say we take the M list as an example. So we have 28 cross 28 and we have one input. So like this we have 32 different inputs. So in one we might have 0 as the input, in some other thing we might have 3 as the input, and so on. We have 32 such kind, right? 32 such data, that is one batch. So this batch goes in, it comes back, and the weight is updated. The next batch will go in, it will come back, the weight again, and so and on and on and on. And finally, when all the batches are completed, that means since we have 60,000 data points here, since we have 60,000 data points and we have a batch size of 32, that means one by one 32 data points will go in, and finally when all the 60,000 data points have gone in once, we will complete one epoch, right? So this is basically what an epoch means. What steps per epoch mean is how many times this happens before we complete one epoch. So we have 60,000 data points. If we divide it by 32, because our batch size is 32, we get this number 1875. So our steps per epoch is 1875. Okay, so this actually gets me a lot. I get very confused with these two, so I did not want other people to get confused, so that is why I explained this part. So we understood what this none means, and we understood the 1875 here. So this can actually be controlled. You can change the batch size. If you change the batch size to, let's say, 64 or something, if you change the batch size from 32 to 64, our steps per epoch will also change. So since we have not mentioned any batch size, it takes 1875 as the steps per epoch. So all these steps get completed. So 1 millisecond per step is basically for each step per epoch. So this goes on and on and on, and you can see we have the loss has decreased. It started from 0.5 and it has come to 0.44, and the accuracy has increased by a massive size, and this has come to 0.88. Now the reason why it did not get better than that, well, a few reasons could be. First of all, I just run this thing for 20 epochs. If I increase the number of epochs, it might be possible that you get more accuracy. The other thing is, see, this data is basically an image, right? But we are not using the entire image, we are flattening this out. So this 2 dimension that we have, the 2 dimension thing, we are not able to actually use the 2 dimension. So it is of basically no use. Until and unless we can utilize both the dimensions differently, it is not going to get very good results. And also there are other neural networks like CNNs that have actually been trained to understand image and the features. So when we will be using CNNs, you will realize that how it actually improves our model and we get very much accuracy. So now this has been done. Now you don't want that every time you run this notebook you have to run the training part again and again. So what you can do is you can save the model. So you have model.save and the model gets saved in mnist model.h5. Now once the model is saved, what we can do is, there is this app called Netron, and what this helps is in, we can actually load the model and see how a model looks like, visualize it. Now I know you might be thinking we have already visualized it here, right? So how is this going to be any different from this? I'll show you. So this is our model. So you have an input layer, you have followed by a flattening layer, then you have two dense layers with sigmoid activation, and then you have a final dense layer with softmax. So let us just click at one dense layer. So here also you have bias training, so you have 10, 5 and 10. For each neuron you have 1, like I mentioned you have 10 neurons here, so for each neuron you have 1 bias, hence 10 bias followed by 5 bias. And you have kernel size, this is basically the input size kind of. Okay, so here you have attributes, you have the type of layer, you have the name for the layer, right? You have the activation, then you have bias initializer, so bias is initialized by zeros. You have kernel initializer, which is Glorot uniform. What kernel initializer basically means is how we have initialized the weights. So are they trainable or not? That means, do we have to train that layer or can we skip that layer? So since we are training that layer, we are using true, and since we are using the biases, we have also done use bias as true. We have inputs, we get the kernel and the bias. If we expand this basically shows all the weights that have been trained. Okay, so this is for the weights. And then again, if you expand this will show all the 10 biases that I was talking about, right? So this layer outputs this. Okay, so this is why this is used. Now you might be thinking, why do we need this? So one of the things is, right now this is a very small model. It comes, and there are times when the model is very big in size, very large in size, and you might actually want to get or understand a more detailed study about the model. In that case, this is very useful. Hence, it is very important to understand this Netron app. So we have trained the model and everything, and in the next class what will happen is, we will go over and understand some other concepts. I will show you how a Google Collaboratory works, and then maybe we can go and understand about different CNNs. CNNs are basically convolution neural networks, and they are used when it comes to images, to understand an image, right? Okay, thank you, that is it, and enjoy learning.